Hello, and welcome to another edition of TutorTube. Today, we will be talking about optimization. So, example 1, a rectangular storage container with an open top is to have a volume of 10 meters cubed. The length of its base is twice the width. Material for the base costs $12 per square meter. Material for the sides costs $8 per square meter. Find the cost of materials for the cheapest such container. So, based on this problem, we need three auxiliary equations that will help us get our main function that we need to optimize. So the three equations that we need, first of all, is the volume equation, the area of the sides equation, and this is special because we have an open top, so there's nothing on the top of this container, and the area of the base. So these three equations need to have the same terms for us to eventually optimize it. So we will be using L equals 2W to make these three equations into the same terms, specifically into W. So we plug in 2W for L for the volume equation, first of all, and then we still have the H hanging around. So we use the 10 and divide by 2W squared, the 10 being the volume of the entire container. So we get 5 over W squared for the volume. Next, we use the area of the sides, and we want to convert all of those terms to be in terms of W. So plug that in into L and into H, and once you simplify this, you will get 20 over W plus 10 over W, 30 over W. And now the area of the base, just plug in that L and you get 2W squared. Now we got to figure out the actual function that we need to optimize. How will we figure that out? Well, remember, the base costs $12 per square meter. The sides cost $8 per square meter. So we will use those two equations, which we derived, 30 over W and 2W squared, to create a total cost function. So $12 per square meter means $12 times the function for the area of the sides, plus $8 times the function for the area of the base. Flip-flop those, so $12 times the area of the base and $8 times the area of the sides. So if you do that, you get 24W squared plus 240 over W. So now we need to actually optimize. So optimization means three things. Take the derivative first of all, then set equal to 0, and then figure out the critical value. So we take it step by step. First of all, taking the derivative yields 48W minus 240 over W squared. So that's power rule and then quotient rule. And then set that equal to 0, factor. You do get an extraneous solution, W equals 0. We don't want that one. So solve for 1 minus 5 over W cubed. And solve for W, you get the cube root of 5. This is the critical value. So we found the derivative, set it equal to 0, and figured out the critical value. Now you plug back into the optimization function, the original 24W squared plus 240 over W, and you find the actual cost of materials that will give you the cheapest such container. So that critical value is the point of optimization, which you will plug into the optimization function. All right, so example 2. Ornithologists have determined that some species of birds tend to avoid flights over large bodies of water during daylight hours. It is believed that more energy is required to fly over water than over land because air generally rises over land and falls over water during the day. A bird with these tendencies is released from an island that is 4 kilometers from the nearest point B on a straight shoreline, flies to a point C on the shoreline, and then flies along the shoreline to its nesting area D. The bird needs 1.5 times as much energy to fly over water as it does to fly over land. Assume that the bird instinctively chooses a path that will minimize its energy expenditure. Find how far point C is from B if points B and D are 13 kilometers apart. So the infamous bird question. So in this aspect of the question, we really only want one part of this entire path. We really only want the distance from B to C. So we need to take it step by step to figure out that distance. First of all, the island is 4 kilometers from the first point B, and B to D is 13 kilometers away. We want to figure out the point from B to C, so we'll call that x. So therefore, the distance from C to D is 13 minus x, or the whole distance B to D subtracted the distance B to C. So 13 minus x kilometers. Also, we can figure out the point from the island to point C, or rather the distance from island to point C, by using the Pythagorean theorem, 4 squared plus x squared, and taking the square root of that. So x squared plus 16 kilometers would be that distance from the island to point C. So all these things we'll use in conjunction with each other to figure out an energy expended function that will represent the bird's path. So the bird needs 1.5 times as much energy to fly over water as is established by the problem. So let's say that whatever energy the bird needs to fly over land is k. Okay, so it would need 1.5 k to fly over water. So we need to figure out the most optimal path for the bird in terms of the bird wants to get to its destination without exerting a lot of energy. So that optimal path would be traveling the hypotenuse of the triangle, which means traveling over that x squared, the square root of x squared plus 16 distance, and then from there traveling from C to D. That would be the optimal path. That will be the optimization function that we create. So how is that expressed? Well, we know that 1.5 k represents the distance over water, or the energy over water that the bird needs. So 1.5 k times the distance it travels over water would give us that distance, or would give us that energy level, and then we add that to the energy it needs to fly over land, which would be from point C to point D. So this is our energy function that we have here. So what do we need to do with this energy function? We need to minimize it. In other words, optimize it. So optimization, again, involves 3 different steps. First, we need to take the derivative. Taking this derivative involves 2 different rules, power rule and also the chain rule. So once you do the chain rule, you get 1/2 times the derivative of the inside. So x squared plus 16, that derivative is 2x, and then you need to raise that to the 1/2 power minus 1. So that's where I get the negative 1/2 from. And then the last part is from the negative kx part when you take the derivative. And remember, k is a constant, so that 13k falls off. Next, after taking the derivative, you might have to simplify it to help you. So this next step is still part of the derivative, we just simplified it. So we simplified it by canceling out the 1/2s and then moving that negative 1/2 to the bottom and taking away the negative. So we're just using our algebra skills here to help us when we have to set things equal to 0. Remember, that's step 2 of the optimization process. So step 1 actually took 2 steps because we wanted to help ourselves later on. And then step 2 is just setting it equal to 0. And then step 3 would be actually finding the critical value. So now we actually have to solve for, in this case, x. Remember, k is a constant. So solving for x, number of different ways. You could move over this k, which I've done here, and then also multiply both sides by that fraction to clear out that fraction to make everything linear. So now we have k on both sides. So when you have k on both sides, or any variable or number on both sides, you can divide both sides by that thing. So k goes away, and we're left with 1.5x equals the square root of x squared plus 16. And I've written it still in this fraction exponent notation just to be helpful when we took the derivative. So now, just more algebra. So now we square. Square both sides, and you get 2.25x squared on the left side. And then if you move over that x squared, you would get 1.25 x squared equals 16. So when you squared both sides, on that right side, the x squared plus 16 to the 1/2 cancels out. And then you're just left with the 16 when you move over the x squared. And now you solve for x by first dividing by 1.25 and then taking the square root. So remember, when you take the square root, it always yields plus or minus. In this case, we're dealing with positive values, distances. So x can only be from 0 to 13, which means that we take the positive, and plugging that in, we get 3.58 kilometers. So we really only wanted one part of this. We wanted the point B to C, and we had to use all these things in conjunction together to figure out that one point from B to C. So 3.58 kilometers. So I want to use this last slide as a quick summary of what we covered today. So with all optimization problems, every problem is different. These are word problems, and there are nuances to every single word problem. So some things you may have to do slightly different than other things. But I'm going to cover some themes that you can keep in mind to help you solve those problems that you encounter. So for the first example that we covered about the open top container, we had three auxiliary equations that we had to use to find the actual equation that we wanted to optimize. So three outside equations that we needed to get to our main equation. But after we found that optimization equation, that's where we actually optimize it. So the hardest part is actually finding the equation itself, and that's where the nuances come in. So the nuance in this first example with the open top was that we needed those three auxiliary equations, the volume and the areas of the sides and the base, to get our actual optimization function. Once we did that, we found the derivative of the optimization function. And remember, that is the first step in optimization. And that's the first step of three. The second and the third is to set it equal to 0 and find the critical value. So optimization involves finding the optimization function, taking its derivative, setting it equal to 0, and determining the critical value. And then in this particular problem, we had to plug the critical value back into the original equation in order to get the desired solution. In example 2, though, the optimization function required sketching the bird's optimal path. So this will come up often, especially if you're not given a picture. You should sketch it. So from there, we needed an auxiliary variable to correctly determine the optimization function. So that was the K energy level that we needed to help us find the function. So once we determine the optimization function, the same theme applies. So we need to go through our three steps again. Once we get our function, we take its derivative, set it equal to 0, and find the critical value. So therefore, the optimization function that we found is optimized. In this case, once we found the critical value, we're done. So this is the nuance of example 2, the bird question. We just needed to stop at the critical value in order to find the solution. Thank you for watching another edition of TutorTube. Check out what else the Learning Center has to offer in the links below.